Hello everybody, in this lecture we will be solving 1996 IMO problem number 1. Here is a view of this problem. We are given a positive integer r and a rectangular board ABCD with dimensions AB equals 20. So that's the point A, B, this dimension here is 20 square wide, and then 12 here for the vertical. And the rectangle is divided into a grid of 20 by 12 unit squares, as you can see here in my picture. The following moves are permitted on the board. One can move from one square to another only if the distance between the centers of the two squares is root r. So root r is the distance from one move to the next. The task is to find the sequence of moves leading from the square with A as a vertex. So starting from this little square here, where A is a vertex, oh, by the way, let me finish the count here. So this is C, and this one here is D. Starting from this square here, we want to end up into this square. That's the goal. So let's start with the first part. Show that the task cannot be done if r is divisible by 2 or 3. To begin with, let's try to describe this clearly here. So if we move from point P to the next point Q, let's say that the coordinates of P are P1, P2, and the coordinates of Q are Q1, Q2. Then the move is a legitimate move if the distance is r, right? So therefore, if we have q1 minus p1 squared plus q2 minus p2 squared, the distance is simply equal to so root r squared, which is r. So therefore, for this, and obviously here I'm considering the centers of these. I'm just locating this square, this rectangle ABCD, such that each unit square has its center on a lattice point, right? So therefore, the Q sub i's and the P sub i's here, the P sub i's and the Q sub i's are integers. You have integer coordinates. Points. You move from one integer coordinate point to another, and the move is a legal move if this condition is satisfied. In fact, we can further call this as x and this one as y. So therefore, in a sense, we have x squared plus y squared is equal to r, where we can consider x and y as the coordinates of the displacement vector. Let me move here. So PQ, if you think of this vector moving from P to Q, that would simply have coordinates x, y, and x and y must be such that x squared plus y squared is equal to r. So this is the condition for a legal move, where x and y here, obviously, they are integers. Now, the first case, so part A, what happens if r is even? So if r is even here, and we have squares on the left hand side, so it implies that either x and y are both even, which works, or x and y at the same time are both odd. So you have two subcases here. So consider the following coloring. If I color this 20 by 12 grid in alternative colors like this, like in a chessboard, right? So I will not do the whole thing, but you get the idea. So then, for instance, what happens if both x and y are even? So the displacement from this point to the next, the difference of the x coordinates is even, and the difference of the odd coordinates. So you are jumping by 2's, and on the y coordinates you are jumping by 2's. So we will end up at another black square, right? If you think of this expanded like a chessboard, you start at a black square, well, in this case a green square. So each legal move will take you to another green square, right? Does that make sense? So you will move from even to even. Well, it's even much more restrictive than that, but let's assume for the moment. So therefore, what's interesting is if you can continue to color these vertices here like this, what will be funny is that, and you probably already guessed, the color of the square in B will be white. So therefore, you are only allowed to jump from black to black such that this equation holds. There's no way that you can end up in B. End of story. So how about if X and Y are odd? Things won't change. So let me show it with a red color. So you start at this point. Let's say that you move 3 to one side, 1, 2, 3, and then let's say 3 up, 1, 2, 3. Ooh, wow, 3 by 3, again we are in a black. Or for instance, if you go 1 by 1 down, 1 by 1, ooh, again black. So therefore, irrespective of if you move both X and Y odd or both X and Y even, you can only jump across among black squares. You will never hit a white square. So as a result, you can think of this like the move of a bishop which is in the game of chess. A black bishop will only hit the black squares. It can never land on a white square. So therefore, it will never land on this corner, and so therefore it is impossible. So when R is even, so what happens if it is divisible by 3? If R is divisible by 3, then in that case, the equation here would imply immediately that X is congruent to 0, and also Y is congruent both, so they are both congruent to 0 in mod 3. The reason is that if X or Y, one of them is congruent to 1 or 2, when you square them, it will give you 1 in mod 3. You square the other one, 1 in mod 3. 1 plus 1 is 2 mod 3. Or if you have one of them 1, 2, the other one is 0, still 1 mod 3 plus 0 mod 3 is 1 mod 3. You will never get 0 mod 3, right? So as a result, we cannot think of the following coloring. For instance, let's now work on this square. Let me move this one, the next one, a little bit down. I will need it later on. So we have again A, B. So I want to start in this one and end up in this one. And this time I will color this whole column as black. And then I will 1, 2, 3. I will color this one as black. 1, 2, 3. This one black. 1, 2, 3, black. 1, 2, 3, black. 1, 2, 3, black. 1, 2, 3, black. And notice that B is on a column which is white color. Now we are only allowed to move displacements of 0 mod 3, right? So you can go up by 3 or 6 or 9, 1, 2, 3. So you can go up 1, 2, 3, something like that. And in a similar way, for the Y, so this is for the Y. For the X, you can again 1, 2, 3. You see what I'm doing, right? You can 1, 2, 3. Let's say you go down, you go 1, 2, 3, 4, 5, 6. So you will only land somewhere on the black column, on a square on this black column. In fact, you will only land in one of these vertices, right? So if you will, you will only land in one of these vertices and never ever on a white colored square. So therefore, if you start at point A, you will never end up in point B. This is another impossibility result for divisibility by 3. So if R is divisible by 2, the game will never end at starting at A, it will never end at B. Again, if R is divisible by 3, starting at A, the game will never end at B. So now let's have a look at the second part. So we are done with the first part. Prove that the task is possible for R is equal to 73. Because it's a possibility result, what we can do is we can just show an example. And let me go ahead and do that actually. So let me just copy this shape one more time. Oops, I'm not allowed to copy it, strangely. Yes, I am allowed to copy it. So let's just, oh, I already have one. Okay, good Lord. So I have this one. In fact, I might need one more. Let me just copy another one here, paste, Okay, so I will make use of this later on. So again, so now we are in part B. Show that r equals root 73 works. So this would imply that r squared is 73. Right. R is, wait a second. So R is itself 73. My bad. So going back, so R is 73, but 73 is simply 8 squared plus 3 squared. So therefore, this gives me an idea about the displacement vector, right? So the displacement vector can be any of the following. It can be anything like plus or minus 8 plus or minus 3, or plus or minus 3 plus or minus 8, or plus minus 8 minus plus 3, or plus minus 8 uh, oh boy minus plus 3. Oh no, that's a 3, that's an 8, sorry for that. Okay, so there you go. So I just need a possibility result, right? So therefore things shouldn't be too hard in this one. Well, until you reach the final thing, right? So you start from here, you want to end up here, and your displacements are one of these. After working several examples, you can come up with the following. I will go to the right by 3, 1, 2, 3, and then up by 8, 1, 2, 3, 4, 5, 6, 7, 8. So I end up in this one, and then I will go to down 3, 1, 2, 3, and then right 1, 2, 3, 4, 5, 6, 7, 8. I'm right now here. Actually, the starting point is 0. Let's call this guy as 1. Now I'm in point 2. Then I'll do the same thing, go down 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. Now I'm at point 3 here. And then I will go to the left 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. I'm at point 4. And then 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. I'm at point 5. Let me do it again. 1, 2, 3 down, 1, 2, 3, 4, 5, 6, 7, 8. I'm at point 6. I'm almost done, guys. Now down 3 again, 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. That's point 7. Then again, right 1, 2, 3, up 1, 2, 3, 4, 5, 6, 7, 8. That would be point 8. 3 by 2. Yeah. And then down 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. That's the point 9. And finally, final sequence of moves. Down 3, 1, 2, 3. Right 8, 1, 2, 3, 4, 5, 6, 7, 8. That's the point 10. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. Whew! In 11 steps, I just showed you a construction how to start from point A, and in 11 steps to reach to point B. So therefore we have proven part B. Now final part C, check for this one as well. Can we do the same thing if R is 97? So let's use the same strategy we did for part B. So let's move this a little bit down. So for part C, we have r equals 97. So the displacement vector x squared plus y squared should be equal to 97. Notice that 97 is simply right. There's only a single representation for 97, and it's just 81 plus 16. So that's the unique representation for that. So therefore, the displacement vectors, right? The translation vector PQ should look like we did earlier, plus minus 9, plus minus 4, and plus minus 4, plus minus 9, plus minus 9, minus plus 4, and plus minus 4 minus plus 9. So we have 8 different legal moves. Right. Okay, so we have these moves available. These are the only legal moves available. And now this time I claim that it is not possible actually to end up with that. So it's not possible to complete the task starting from point A, ending up from point B. And the way I will do it, this time I will color it in the following fashion. So I will go 4 by 4, 4 black here, followed by 4 white, followed by 4 black. Then I have 4 black squares here. So I'm coloring my grid. This is a standard now, right? So we've solved quite a few in this series, IMO Problems and Solutions series. We have solved quite a few problems using this coloring scheme. Right, so let me finish up with this. Almost done. By the way, if you guys are into combinatorics, I highly recommend the Sriram notes available on AOPS. These are great, wonderful notes that will significantly help you with your combinatoric skills. Okay, so we have our coloring. So we want to start from this cell A, which is black color, black. And we want to end up at point here, B. And this one is a white one. It's white color. I claim that if R is 97, these legal moves, which starts at the black color, will always end up somewhere on a black color. So let's start by investigating these vectors and these displacement vectors first. So 9 to 4, right? So if I go right by 9, 1, 2, 3, 4, 5, actually let's change the color. Yes. So 1, 2, 3, 4, 5, 6, 7, 8, 9 by 4. 1, 2, 3, 4. Ooh, that wouldn't work. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. That won't work either. Or I can go up by 9. Well, I can't go in the minus on this particular example, but at least you see what's going on. If we were by any chance on any other black square and we decided to go by 9 to the left, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 4 down, 1, 2, 3, 4. Again, the same story happened. Or if you went, let's say that we started again here, we went 4 to the left, 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, a black. So therefore, you start at a black, you always end up at a black using any of these vectors. Similarly, you start at a black, use any of these. Again, you will end up at a black. So therefore, this coloring clearly shows that you with these moves you can only legally go from black squares onto the black squares. You will end up in sequences of black squares, never ending up on a white square. And this shows the impossibility that, so this thing impossible. The task in this case is simply impossible. And that solves this beautiful problem. Hope you enjoyed this lecture and looking forward to see you guys in our next lecture.